Well, welcome. Today we're going to talk about hyperbolic trig functions. Hyperbolic trig functions are an optional thing. Some of the classes are not covering this semester because they don't actually teach you how to do any new integrals, which is what we're about in this chapter. But they do teach you how to do some of the integrals faster. And there are lots of textbooks that refer to them, and you don't want to be unaware what they're talking about when you see it. So we'll see this to improve our speed on some of the integrals with square roots in them that we had in the last section. And we'll do these so that we can read the literature also. So here they are. Hyperbolic sine of x, called sinh x, is defined to be e to the x minus e to the minus x over 2. So it's defined in terms of functions we already know. It's just a convenient thing that comes up a lot, and it's no new functions whatsoever. We just make this definition. Similarly, the hyperbolic cosine is e to the x plus e to the minus x over 2. And all the other trig functions then follow if you just assume that they have the usual reciprocal and quotient relationships that they do in ordinary trigonometry with circular trig functions. For instance, in circular trig functions, tangent is sine divided by cosine. Here, hyperbolic tangent is sinh divided by cos, right? The twos cancel and you just get e to the x minus e to the minus x over e to the x plus e to the minus x. So there's hyperbolic tangent. And then these three are just their reciprocals, right? Hyperbolic cosecant is the reciprocal of hyperbolic sine, just like cosecant is the reciprocal of sine. Hyperbolic secant and hyperbolic cosine are reciprocals of each other. Hyperbolic cotangent and hyperbolic tangent are reciprocals of each other. What's more, these even have a lot of the identities that the ordinary trig functions do to something kind of close. For instance, if we have in trig sine squared plus cosine squared equals 1, in hyperbolic trig functions we have cos squared minus sinh squared equals 1. So this corresponds to the Pythagorean identity of trigonometry. You just put a minus instead of a plus here. And you want to memorize that one, and you want to memorize all these definitions. I think it's kind of useful to know whenever you learn a new function, kind of what it looks like. So I'm going to run this over to the side here for a minute. Here's a graph of some of them. What do these look like? Well, one way to figure out what they look like is to plot this function e to the x and this function e to the minus x and say, well, sinh x is 1/2 this one plus 1/2 this one. So this thing actually goes out here and it asymptotically approaches 1/2 of the value of this e to the x function, right? In fact, if you plotted e to the 1/2 e to the x, it would come through here at 1/2. And this hyperbolic sine would come closer and closer because after all, hyperbolic sine is 1/2 e to the x plus 1/2 e to the minus x, a term that goes to 0 as x gets larger and larger. So sinh asymptotically approaches 1/2 e to the x on this side and similarly approaches 1/2 e to the minus x on this side. Cos, if you plot it, it's not shown here. It comes down here, it looks like this. Because it's the sum of 1/2 e to the x and 1/2 e to the minus x, this one plus this one over 2. And so it on this side also approaches 1/2 e to the minus e to the x, and on this side it approaches the other one, 1/2 of this one on the other side. So that's what they look like. Sinh looks like this, which is 1/2 this one plus 1/2 this one. Cos looks like this, approaching the same asymptote on this side and approaching 1/2 e to the minus x on this side. Those are the only two I really expect you to know. Their graphs. Furthermore, there's some other properties. We found out that when we were doing trigonometric integrals, trig identities were a valuable tool. There are some identities here that also help. I won't ask you to memorize these. I think what you do is just recognize these are here and you recognize a few basic identities. If you really need these, you look these up. because these are not all that commonly used. They're one of the lesser important sections, but you do have to kind of see them, right? So let's say, suppose I wanted sine A plus B, then it's sine, cosine plus cosine, sine, right? What about hyperbolic sine of A plus B? Similarly, sinh cosh plus cosh sinh, same thing, just put an H on each of these functions. This then leads to a double angle identity. Sinh of 2A, if you put B equals A, is equal to 2 sinh A cosh A. So it has a similar double angle identity. And also cosh of A plus B. Now you start to see a few differences. Is cosh plus sinh. So the minus from ordinary trig double angle identity becomes a plus. There's a little difference here. One of the troubles is they're almost the same as trig identities. They're almost easy to memorize, but alas, these occasional minus sign changes make it a little difficult. I want to give you some hints how to do this, though. Anyway, here's the identities that are useful. From these, you can figure out the double angle identities, right? Just put B equals A. And so this actually is pretty useful, but I'll say you don't really have to memorize those. I'll put them on the test if you need them. Now, what about derivatives, right? We're about calculus with these things primarily. So what about these? What could be the derivative of the hyperbolic sine of x? Well, we only have one thing to go by right now, right? It's the definition. E to the x plus e to the minus x over 2. I'm taking the derivative of that. Wait a minute, I can do that from elementary calculus, right? Calculus 1, I'll say derivative of 1/2 e to the x. I pull the 1/2 out and take the derivative of e to the x, right? Derivative of 1/2, oops, this is minus. Minus 1/2 e to the minus x is minus 1/2 derivative of e to the minus x, right? So you take the derivative of the difference is the difference of the derivatives and pull the 1/2 out in each. And now the derivative of e to the x is just e to the x. Derivative of e to the minus x, right? That's e to the minus 1 times x, so its derivative is minus 1 e to the minus 1x. I get minus a half minus e to the minus x. And this all adds up to e to the x plus e to the minus x over 2, which notably is the hyperbolic cosine. Oh, the same identity, just with an h on it, right? Derivative of sine is cosine, derivative of sinh is cos. However, similar proofs, you just do the same kind of thing. You know the derivatives of the exponentials, so you can do all these derivatives by writing their definitions. But if I take the derivative of cos, I find there's a little difference. The derivative of cos actually turns out to be plus sinh, right? Derivative of cosine is minus the sine, but derivative of cos is plus the sinh. Also, hyperbolic tangent has derivative hyperbolic secant squared, just like in circular trig functions. Derivative tangent is secant squared. Hyperbolic cotangent has derivative minus hyperbolic cosecant squared. But now comes a difference again. The derivative of hyperbolic secant is minus hyperbolic tangent, hyperbolic secant. That's different from a minus sign from what you study in circular trig functions. And finally, derivative of hyperbolic cosecant comes out to be minus hyperbolic cotangent, hyperbolic cosecant, just like with circular trig functions. So you want to memorize these 6 derivatives. They're easy. The only thing you have to realize is that 2 of them have minuses. Which 2? That always makes it very difficult, right? So star means memorize. Well, here's how I like to think of it. You can come up with your own device, maybe. It's cosh and it's reciprocal hyperbolic secant that have the minus sign different. Otherwise, they're all just the same. Put an h on them. So cosh and its reciprocal hyperbolic secant. This should be reminiscent of something you've seen in trigonometry, right? even and odd functions. Just like every trig function is even or odd, every hyperbolic trig function is even or odd. And kind of a neat thing because most functions aren't even or odd, right? Remember even functions and odd functions? F of x is odd. What does that mean? That means if you take f of minus x, you get minus f of x. So every odd power of x is an odd function, for instance. If I took y equals x cubed, looks something like that. That's an odd function. If you replace x with minus x, you get minus x cubed, right? So f of minus x is minus f of x. Every odd function has symmetry through the origin, right? Remember that if you have f of minus x is minus f of x, that says if you have any point on here, x, y, then you have a corresponding point. When you replace x with minus x, you get minus y. So you get minus x, minus y is on the graph whenever x, y is, which means that every sister point of an odd function, or every odd function has a sister point straight the opposite distance through the origin. So this point has a corresponding point down here and so on and so forth. That's a property of an odd function. And you notice that on the graph of hyperbolic sine over there, it went through the origin much like this and had corresponding points on the opposite side of the origin. Odd functions have some symmetry through the origin. F of x is even by definition if f of minus x equals f of plus x. The minus goes away. So an odd function, the minus comes out. F of minus x is minus f of x. Even function, it goes away. F of minus x is the same as f of plus x. And this has, it's a little hard to get the picture in here, this kind of property, y equals x squared is a famous even function. Any even power of x is an even function, right? So there's y equals x squared. What kind of symmetry does it have? Well, it says f of minus x is the y coordinate minus x is the same as the y coordinate plus x. So you have a point here, x, y. You have to have a corresponding point over here, minus x plus y, right? And so this one has a symmetry through the origin. If this point is here, same distance the other side, you have another point. Flip it over the y-axis, it lands on its side. So that's a symmetry of an even function. And hyperbolic secant and hyperbolic cosine are even. All the rest of them are odd, have symmetry through the origin. That's kind of a useful thing to recognize once in a while. But you see how these things work. Now, maybe you remember even and odd functions, and you can figure it out for these too. Every hyperbolic trig function is even or odd. Turns out that just like with regular trig functions, where cosine and secant are the even functions, the other four are odd. And I always thought, shouldn't there be three evens and three odds, just like on a diet or something? You have six-sided die and three or even three. No, it is asymmetry. Why? That always bugged me. But there's two even functions, cosine and its inverse, its reciprocal, secant, and all the rest are odd. So four odd and two even. Same thing here. The same functions are even or odd. All six of these are either even or odd. Hyperbolic cosine and its reciprocal, hyperbolic secant, are even functions. And they also have this property, the derivatives are off by a minus. So that's how you remember how to switch the minus signs on these things. The derivatives are off by a minus on hyperbolic cosine and its reciprocal. And those are the two even functions also. All the other are odd. All right, so there are some useful properties, but we aren't really studying derivatives in this chapter. We really want to study integrals. That's why we brought this up. So I'll mention that these imply corresponding integration results, right? For example, if the derivative of sinh is cosh, then it ought to be that the integral of cosh is sinh to within a constant, right? And if derivative of cosh is sinh, right, then the integral of sinh x ought to be cosh x plus a constant, and so on down the line. All these integral formulas, you don't memorize them themselves. If you remember these, then you'll recognize some of those others. Like if you see integral of hyperbolic tangent times hyperbolic secant. You say, wait a minute, that was in circular trig functions, the derivative of secant. And now again, this will be just off by a minus sign. So the integral of hyperbolic tangent hyperbolic secant will be minus hyperbolic secant. Right? It's just a regular one from trig with a minus and h's on all these things. So bear that in mind, and you can do a lot of these integrals. Let's do a few examples then. Suppose I wanted to find the integral of 3 hyperbolic sine 2x plus 1 with respect to x. Right? How do I do something like that? You look at it and say, how is that similar to the circular trig functions? If I had 3 sine 2x plus 1, what would I do? Oh, I just say it's a function of a function. I'll let u be the inside function, and maybe that will make the integral easier. Furthermore, it's got a constant multiplier here. I'll pull that out. So I'll say this is equal to 3 times the integral, pulling this out, hyperbolic sine, and I'll replace this with u. Right? And now what do I do with the rest, right? It's differential du satisfies du dx dx, the derivative times dx. Well, du dx, the derivative of u is 2, so this is 2 dx. And again, if du is 2 dx, then I divide by 2 and find out the 1/2 du can replace dx directly. So I scratch this out and put 1/2 du. I scratch this out and put u, right? Scratch them out. And it's substitution. 3 integral hyperbolic sine u 1/2 du. There it is. Now integral of hyperbolic sine is hyperbolic cosine, because remember, it's sinh is the derivative of cos, right? So this must be 3/2 integral of sinh u is cos u plus a constant when I drop the integral sign, right? And then u I have to put back was 2x plus 1, so it's 3/2 sinh 2x plus 1 plus an arbitrary constant. There we go. There's an easy integral for the hyperbolic trig functions. These things come up once in a while. You want to be familiar with them, right? Moreover, when you get harder groups of these, like powers of sinh times powers of cos, you can follow rules analogous to those that we did for the circular trig functions. For instance, what if I had this one? What is the integral of hyperbolic sine squared of 4x? I wonder what that is. You could substitute u equals 4x and rewrite this. That's not a bad idea, but it's not necessary actually. So I'm going to skip it. Instead, I'll say, what would I do if I saw sine squared instead of sinh squared? I remember it's a half angle identity or a reduction formula. On the test, I'll give you the reduction formulas. I don't want you to memorize those, but you should memorize the half angle identity, right? And you can use either one. The half angle identity for hyperbolic trig functions is a little different. It says, rewritten for the half angle identity solved for sinh squared, says that sinh squared can't be replaced by cos squared cos 2x minus 1 over 2, right? If this was a trig function, say sine squared is 1 minus cosine 2x over 2. This one, you just replace it with h, but you also switch the minus sign again. So you have to, like I say, you don't have to memorize this. I'll give this to you on the test if you need it. But you do want to know that there is a half angle identity for dealing with this, right? So you rewrite this with that substitution as cos of twice this angle. I should call this u here. And if I put u equal 4x, then sinh u equals cos 2u minus 1 is cos 8x minus 1 all over 2. Well, I know how to integrate that, right? The 1/2 comes out. Integral of cos 8x, what was that? Well, integral of cos was sinh, but this is integral of cos, not cos x, but cos kx. Just like integral of cosine kx Remember that one? By u substitution, u equals kx, you found out it is 1 over k sine kx plus a constant. So integral cosine x is sine x plus a constant. Integral cosine kx by u substitution is 1 over k sine kx. We need this so often that we memorize it. Exactly the same thing here. If I want to integrate cos 8x, I get 1/8 sinh 8x. And then if I want to integrate minus a half, I just get minus a half x. There it is. In analogy to this rule for circular trig functions, hyperbolic trig functions give you this. And by the way, sometimes they'll just call them hyperbolic functions. Hyperbolic trigonometry is a long phrase. At least cut half of it out, right? So what do we wind up with in here? 1/16 sinh 8x minus a 1/4 x plus a constant. Put on there. And this is kind of important to know because sometimes you go on one of those online calculators and it'll give you as the result an inverse hyperbolic trig function or a hyperbolic trig function. You go, what is that, right? So you want to see this section so you know what it is. That's what they are. You saw the definitions at the beginning. But you can integrate these powers of sine times power of cosine by the same trick, right? Sin times cos to powers. If one power is odd, that you equal the other function, right? And the sin to a power times cos to a power. Same trick applies there. So we can do all those. And what's more, there's an interesting geometry thing out of this. Maybe I should mention just in passing. In fact, you remember from trigonometry, when you have the unit circle, every point on the unit circle, so this goes out to 1 and 1, is such that if you take a ray from the origin through that point, the point has coordinates cosine x, sine x. So if you let x run from 0 to 2 pi and plot cosine x, sine x, you'll sweep out this unit circle once as x goes from 0 to 2 pi. What happens if in the plane you were to plot all the points cos x, sinh x? I recommend you look online at some of these things like Wikipedia and Wolfram and so forth. Just Google hyperbolic trig functions, look them up. There are lots of neat properties like this that come out if you look on the page. And what this comes out to be, just like this comes out to be a circle, and you get circular trig functions, with the hyperbolic trig functions, you get a hyperbola. Like that. This is the circle x squared plus y squared equals 1. This is the hyperbola x squared minus y squared equals 1. How about that? You let x go from minus infinity to infinity and you sweep out this one branch of it. Hyperbola actually has another branch over on this side that also satisfies this equation. But just like this is a circle at 0 of unit radius, you can think of this, it passes through 1 here and minus 1, as a circle at infinity of unit radius in some sense, and they're sort of related in a nice way. What's more, there's nice relationships in terms of the imaginary unit. I is the square root of minus 1. You get wonderful relations like this. Sine x is equal to e to the I x minus e to the minus I x over 2I. And cosine x is e to the I x plus e to the minus I x over 2. These kinds of things show you that actually when you replace, right, this looks like hyperbolic sinh of I x, right? And so sine and hyperbolic sine are intimately related through the imaginary unit. You can look up all those things online. I don't care if you memorize those or not. They're just kind of fun. I think if you see a few of those, you get an appreciation for the beautiful symmetry between these things. Well, what's most important for us for this section is not just to be able to integrate these. I want you to be able to do these integrals of hyperbolic trig functions, but to be able to do integrals involving square roots. Remember in the last section, some of those problems were pretty nasty. We had to use trig substitutions to solve those things with square roots in them. And we can make a clever substitution with a lot of work, and some of them we can come up with a very complicated answer. what these hyperbolic trig functions will do for you, they'll cover exactly what were the bad square root cases last section and give you an easier route. And here's how we do it. Inverse trig functions. How do you find the inverse of any function in algebra, right? Remember, you do two things to find the inverse of an invertible function. They're not all invertible. They have to pass a horizontal line test. No horizontal line intersects them more than once. To find the inverse of an invertible function, y equals f of x, you had a two-step method, right? Anybody can do the two-step. One, you write the reverse, because the inverse relation just reverses the x and y coordinates, maybe you remember, which flips the graph over y equals x. It's kind of a neat symmetry, but it's, we don't want to spend too much time on that in this class. But you write x equals f of y, and then you solve for y, and that's how you find the inverse of any invertible function. So we can try that with the hyperbolic trig functions. For the inverse of y equals hyperbolic sine of x, we go to step one and we write x equals hyperbolic sine of y, right? Which by definition is e to the y minus e to the minus y all over 2. Now, we solve for y, right? And then we'll have the inverse function. So let's multiply this through by 2 and write that 2x is equal to e to the y minus e to the minus y. Then we can subtract 2x across and get 0 equals e to the y minus 2x minus e to the minus y. So I subtract 2x from each side. And now I multiply by e to the y and get 0 equals e to the y squared minus 2x e to the y minus 1. And I put this up here not because I'm going to ask you this on a test, but because this is a useful technique that you'll see again. What if we got here, if we put u equals e to the y, this is 0 equals au squared plus bu plus c. It's a quadratic equation in u equals e to the y. So I can solve this with a quadratic formula, right? I can say that u, or e to the y, is equal to minus b, which is minus a minus 2x or plus 2x, plus or minus square root b squared is minus 2x squared minus 4 times a times c, all over 2a. So by the quadratic formula, we find e to the y. Well, that's equivalently e to the y equals, and we can simplify this, 2x over 2 is x. And actually for this, we want just the plus sign, it turns out, plus, right, this won't be a function if we use both plus and minus, and the inverse ones use the plus. This square root is square root 4x squared plus 4, and it's over 2. Well, you can take 1/2 the top over 1/2 the bottom. That'll, the 1/2 on the top can go under the square root as a 4th and get rid of those 4s, and you come up with e to the y is x plus square root x squared plus 1. How about that? Now you take the logarithm of each side to get rid of the exponential, right? ln of e to anything is just that thing. So ln of e to the y is y. On the left is equal to ln of x plus square root x squared plus 1. And there we have, this box, just this part. There we have inverse hyperbolic sine of x. How about that? Just like the hyperbolic functions were just defined in terms of the exponential you already know. Their inverses are defined in terms of the inverse of the exponential, the logarithm, and square roots. It turns out all these hyperbolic trig function inverses are just logarithms and square roots, and so they're nothing new either. Why do we need them? It's partly to speed up our process now, because now we'll just say similar formulas apply for other hyperbolic functions, inverses. I won't write them all out. It's not important that you know them. You just recognize them in terms of logarithms and square roots, and you can look them up when you need them online quickly, right? If you need those on the test, I'll give them to you. I don't think you'll even need them. But here's what they can do for you now. For instance, suppose I wanted to do this integral. Pull it off of here. Let me do one more thing first. Sorry. What you can do now is compute the derivatives of these things. Once you know that the inverse hyperbolic sine, for instance, is this function, you can take the derivative of this function with your calculus 1 techniques, and it's pretty messy, right? Because it's got a chain rule in there and 2 chain rules actually, and a bunch of work along the way. But we'll say with work, with calculus 1 work, you can calculate the derivatives of the inverse trig functions. You'll find that the derivative of the inverse hyperbolic sine of x, by using that formula, is the derivative of natural log x plus square root x squared plus 1. And with a bunch of work, this just comes out to be 1 over square root x squared plus 1. There's the derivative of the inverse hyperbolic sine. Derivative of the inverse hyperbolic cosine is similarly 1 over square root x squared minus 1. This was the bad case before, right? In the last section, if you had 1 over square root 1 minus x squared, that was just the derivative of arc sine, but 1 over square root x squared minus 1 you didn't have. You had it with an x outside if you wanted to do secant or something, but that was the tough case. Well, now look, it's a lot easier. Similarly, inverse hyperbolic tangent x, oops, this is derivative, has derivative 1 over 1 minus x squared. Well, it applies when absolute value of x is less than 1. That's where inverse hyperbolic tangent is defined. Similarly, the inverse hyperbolic cosine is 1 over 1 minus x squared also. How can that be? Oh, it's for absolute value of x greater than 1. And then these are defined, obviously, when x equals 1. But that does point out that when you want to integrate these things, you can get either one of these two things. Integral 1 over 1 minus x squared is this one. If you're integrating on an interval where x, absolute value of x is less than 1, can't pass through 1, it's not defined there, but it's got a vertical tangent, basically. And then if you're on an interval where absolute value of x is bigger than 1, the integral of this is inverse hyperbolic cotangent. Anyway, so you've got those kind of things. Then the inverse hyperbolic secant of x has derivative 1 over x square root 1 minus x squared. Remember, derivative of secant was 1 over x square root x squared minus 1, absolute value here. And then arc hyperbolic cosecant has derivative 1 over absolute value of x square root 1 minus x squared. All right. So there's some important properties that will help us do integrals, because now you recognize that if you see an integral of this, you just immediately write inverse hyperbolic sine. In the past, this was hard to do. Here's an example. And suppose I wanted to evaluate this integral. One over square root 1 plus 3x squared dx. Well, that's no good. Last section, what would I do? I might change it first by multiplying top and bottom by a third. And say this is the integral of 1/3 over, if I take 1 over square root 3 on top and bottom. If I take 1 over square root 3 times the bottom, the 1 over square root 3 can come inside as a 1 over 3, and we'll get square root 1/3 plus x squared. All right. So you would do this one. This is last section. And then at this point, you say, oh, 1 over x, or square root x squared plus a squared. I could try substituting x equals a, which is 1 over square root 3, tangent theta. And that works. Dx equals the derivative of that, so on. Make the triangle, the right triangle picture. And it takes a lot of work. And when you come out, you get a big mess with logarithms and square roots. Guess why? It's because it's easier using inverse hyperbolic trig functions. So we'll say that's longer. Alternatively, we could say this. Let's rewrite this. Look, it looks almost like the one I just had, 1 over square root u squared plus 1. If only this, instead of being 3x squared, was u squared integrated with respect to u. Well, why can't I make it so with a substitution? I'm, instead of doing this and using the trig substitution, I'm going to let u squared equals 3x squared. So now this will be a square root that looks like this one, right? This means that I want to let u equal square root 3x as the real substitution, in which case du is the derivative of that square root 3 times dx. So let's make this substitution in here and write this as integral 1 over square root 1 plus u squared. I made it so, right? And then dx gets replaced by 1 over square root 3 du. According to this, just dividing both sides by square root 3. Wait a minute, if I pull the 1 over square root 3 out, this is easy, right? Integral 1 over 1 plus u squared is just going backwards, inverse hyperbolic sine of u. Plus a constant. There it is, just as quick as that. All those many steps over there are made easier. What this does is it takes the very, as mentioned before, the very square roots that were hard last section, makes them a little easier, right? So you'll see some of the integral calculators do this kind of thing. Now we got to put back our secret u here is actually square root 3x. So you got a homework problem like this, and that's how you do it. Let's try one more, and that'll get us a pretty good start on the homework. Then we'll see if you have any questions next time. Suppose I wanted to evaluate the integral of 5 over 16 minus x squared with respect to x, right? Last section, I could do this. I can think of this as square root 16 minus x squared squared. So previously, with much labor, I could make a substitution. X equals a, which is 4 sine theta. All right, and then dx is 4 cosine theta, d theta, and so forth. That takes a lot of work, but it does get the answer. What if we use hyperbolic trig functions? Maybe this would be easier, right? Well, I know if it was 1 over 1 minus x squared, how to do it. So I just got to fix it somehow to make it that way. Let's do it this way. If I just had like 16 u squared here, then it would be 1 minus u squared times 16 on the bottom. So what I want is x squared equals 16u squared. It must be I want x equal 4u. In which case dx is the derivative 4 times du, and 1/4. Yeah, okay. And so now dx I'll scratch out and put 4 du. X squared I'll scratch out and put 16u squared, and this becomes integral 5 over 16 minus 16u squared 4 du. Now I'll just pull all those ugly constants out of there, right? 5 times 4 is 20. Over 16 I can factor out of the bottom. Integral 1 over 1 minus u squared du. Well, this is just 5/4 on the outside. Integral 1 over 1 minus u squared. If we look back here, going backwards on the derivative is just hyperbolic tangent inverse u plus a constant, where u was, oops, 1/4 x. And so this is if its argument, 1/4 x, is between plus and minus 1. Right, let's say absolute value of that is less than 1. Or you could get 5/4 hyperbolic, inverse hyperbolic cotangent 1/4 x, if absolute value of 1/4 x is bigger than 1. So there it is. There's actually two different ways that can come out. Nonetheless, this is a whole lot easier than the triangle substitution. So that gives you a nice introduction to how these things are used in practice, and how to simplify a little bit of your work with those integrals involving square roots.